Welcome to the Deep Dive, the show that cuts through the noise and gets you straight to the most important knowledge and insights from a stack of sources. It's truly wild when you think about it. The speed at which artificial intelligence evolves, it really feels like, I don't know, every few years a new algorithm pops up. It becomes this absolute superstar. Everyone's talking about it. It dominates the conversation. And then maybe it fades a little from the immediate spotlight, but it leaves this huge mark, right? It shapes everything that comes next. It's this constant, really exhilarating cycle. Innovation, refinement. Today's big thing is tomorrow's history lesson. Today, we're doing one of those deep dives into a superstar from, well, the not too distant past, support vector machines, SVMs. Think of this as your shortcut to getting really well informed about a crucial, absolutely vital chapter in machine learning history. We're talking about the algorithm that for quite a while was genuinely considered the gold standard of machine learning. It really earned its stripes as the superstar algorithm of the 1990s and early 2000s, a time when, the dreams of AI were big, but the tools still being forged. So our mission today, explore how SVMs actually worked. How did they separate data into different categories? We'll get into concepts like hyperplanes and why they were such a giant leap forward. We'll dig into why they were so incredibly powerful for tackling those really complex challenges, especially with what's called high-dimensional data. Think massive amounts of text or really intricate images, stuff that had previously just, stumped people. We'll also delve into the mathematical beauty of their kernel trick. Sounds fancy, but it massively expanded what they could do, letting them solve problems that looked hopelessly tangled. We'll touch on the industries that jumped on board, leveraging SVM power, and then, look at the limitations, what eventually paved the way for the neural networks we see dominating today. It's a whole journey, really, from basic ideas to breakthrough applications, and then, the natural way science progresses.
That's a great setup. And you're right, to really appreciate the impact, the sophistication of SVMs, we absolutely need to understand where they came from. We need to kind of rewind a bit, understand the landscape, the challenges that earlier attempts at pattern recognition ran into. And this journey, like so much in AI history, it often starts with a concept that feels fundamental now, but was revolutionary then, the perceptron. It laid some of the earliest groundwork in neural computing, but ultimately it wasn't quite enough.
Okay, let's unpack that. When we talk about those very early dreams, machines learning, recognizing patterns, where does that story actually start? What did that first kind of spark look like?
Well, a really significant spark came from the work of Frank Rosenblatt. Back in 1957, he invented what we now call the modern perceptron. That was a truly pioneering achievement. And then, crucially, a few years later, 1960, he proved the perceptron convergence theorem. Now, what was a perceptron? Imagine it as a very, very simple decision-making machine, really abstract. These early models, they made binary decisions, yes or no, cat or not a cat, that sort of thing. And they did it by essentially adding up evidence, lots of small individual inputs or experiments. Think of it like a simple voting system. Each piece of input data gets a vote or a weight, and the perceptron just sums these up to make its final call. The underlying concept, though, that was seen as incredibly important because many more complicated machines that came later, they shared this basic idea, this summing of weighted evidence. It felt like a real tangible step towards understanding how machines could process inputs, make decisions. A first glimpse, really, at teaching computers to learn from data. The excitement back then was palpable. People genuinely thought, okay, this is it. This is the blueprint for intelligent machines.
Right. And for a time, it must have seemed like perceptrons were the path forward, hinting at this future where machines could, see and understand even in a basic way. But as often happens in science, right, those crucial limitations start to surface. And they cast a pretty big shadow, didn't they? Scald things for quite a while.
Yes, and this raises the key question. What were those limitations? Why were they so significant? The answer, in large part, comes from a really famous and at the time pretty devastating book. It was called Perceptrons by Marvin Minsky and Seymour Papert, published in 1969. They played a pivotal role. They highlighted these constraints, and they did it mathematically. They showed that single-layer perceptrons, just by their fundamental nature, could only represent linearly separable concepts.
Okay, linearly separable concepts. That sounds technical. Can you break that down? What does that actually look like practically?
Sure, let's visualize it. Imagine you've got a scatter plot, dots on paper. You're trying to separate them into two groups, say red dots are apples, blue dots are oranges. If you can draw one single straight line on that paper to perfectly divide all the red dots from all the blue dots, that data is linearly separable. A perceptron, it could handle that. Easy.
Okay, simple enough in 2D.
Right. Now extend that. 3 dimensions. Imagine trying to separate those apples and oranges inside a box. that dividing line, it becomes a flat plane, like a sheet of glass slicing through the box.
Makes sense.
And if you go to even higher dimensions where your data might have hundreds, thousands of features, like classifying documents based on word counts, that flat dividing surface gets a fancier name, a hyperplane.
So Minsky and Papert's big critique was this. If your data wasn't arranged nicely, if it couldn't be perfectly split by a single straight line or a flat plane or a hyperplane, well, a single-layer perceptron just couldn't classify it correctly. It was fundamentally stuck with simple, clear-cut divisions.
So like trying to separate, I don't know, a circle of red dots inside a ring of blue dots. Exactly. You can't do that with a single straight line. Impossible. And the real world, of course, is full of problems like that. Non-linearly separable problems are everywhere. The impact of this critique, it was profound. It contributed significantly to what people later called an AI winter. And it wasn't just the linear separability thing. Minsky and Papert also, and this was important, they lamented the field's lack of mathematical rigor when it came to multi-layer networks. These were theoretical ideas, ways maybe to get around the single-layer limits, but back then they just lacked solid theory, efficient ways to train them.
So double whammy, really. Simple models limited, complex ones not understood well enough.
Precisely. That combination, clear limits for simple models, perceived lack of rigor for complex ones, it really contributed to the demise of early perceptron research efforts. It created a huge hurdle. Funding dried up, optimism faded. It sent researchers scrambling, looking for radically new, more powerful approaches.
And that search, that need for something more powerful, especially for data that wasn't linearly separable, which, let's be honest, is most real-world data, right? That created this clear, urgent challenge. The perceptron showed promise, yeah, but it was like a talented rookie who could only play on a perfectly flat field. The real world is bumpy, messy. It needed something else. And it was this gap, this limitation, that really set the stage for the innovators. It paved the way for support vector machines to just burst onto the scene, ready to tackle that messy terrain. This is where the SVM superstar story really kicks off.
Indeed it does. SVMs arrived as this robust, mathematically really elegant solution to these classification problems. They embodied what the academic work calls new support vector algorithms. You see references like Shulkoff et al. From 2000 talking about this. They just offered a much more sophisticated way to draw those dividing lines, or more accurately, those hyperplanes, allowing for much more nuance, much more effective separation, even in really tough cases. At their core, an SVM's main goal is pretty straightforward. Find the optimal hyperplane, the one that best separates different categories of data points, even if those points live in a really high-dimensional space.
Okay, optimal, what makes it optimal? Perceptrons sound aligned, right?
Right, but SVMs don't just find any separating hyperplane. This is the absolute key, the maximum margin principle. It's a cornerstone of SVM theory. SVMs find the hyperplane that maximizes the margin. What's the margin? It's basically the biggest possible gap, the widest street between the hyperplane and the closest data points from each class. And those closest data points, the ones sitting right on the edge of this buffer zone, they're incredibly important. They're called the support vectors.
Oh, hence the name. They literally support the boundary.
Exactly. They define where that optimal boundary lies.
So it's not just drawing a line. It's drawing the best line, the one with the widest possible buffer zone between the different groups. That sounds like it would make the whole classification much more reliable. Like setting up a really solid no man's land around your decision boundary.
Precisely. You've nailed the core idea. Maximizing this margin is hugely significant. Why? Because it directly helps improve the model's generalization capabilities.
Generalization.
Yeah.
Meaning it works better on new data it hasn't seen before.
Exactly. It performs much better on new unseen data rather than just sort of memorizing the examples it was trained on. It also increases the model's robustness. It becomes less sensitive to small changes or noise in the data. It makes the classification more stable, less, jittery. And this wasn't just some nice theoretical property. It was a fundamental shift. It made SVMs vastly more reliable in the real world. It gave scientists, engineers real confidence that their models wouldn't just work in the lab, but would actually hold up when faced with new, messy, real-world information. This theoretical elegance combined with that profound practical benefit. That was absolutely key to their rapid success and why they became such superstars.
Okay, so margin maximization is huge.
Right.
But what also made SVMs especially revolutionary, you mentioned, was how they handled this thing called the curse of dimensionality. That phrase always sounds kind of ominous, but it describes a real persistent problem for lots of algorithms, right? Like a hidden trap when data gets complex. Did SVMs have a special knack for dealing with that?
They absolutely did. And it was a massive advantage. If we connect this to the bigger picture, the curse of dimensionality, it describes this pervasive issue in machine learning. As you add more features, more dimensions to your data, the data points themselves become incredibly sparse. Analyzing them, finding meaningful patterns, it just gets exponentially harder.
Sparse, like spread out further and further apart.
Exactly. Think about trying to find a specific friend in a tiny, crowded room. Easy. Now imagine trying to find them alone in a huge football stadium. Harder. Now imagine an entire desert. As you add dimensions, your data points become like those lonely individuals scattered across this impossibly vast, mostly empty space. That's the curse. It's like trying to find a needle in a haystack, but the haystack itself keeps getting infinitely bigger with every new piece of straw you add. Makes finding connections, finding separations really, really tough. You see sources like pattern recognition and machine learning, I think it's around page 33, and the elements of statistical learning, pages 22, 26. They explicitly talk about this as a major hurdle.
Right. And for things like images or text, the number of dimensions can explode, can't it?
Oh, absolutely. Take images. Each pixel can be a dimension. A simple 100 by 100 pixel image. That's 10,000 dimensions right there. Analyzing text. Each unique word, maybe even short phrases, could be a dimension. You're easily talking hundreds of thousands, maybe millions of dimensions. Traditional methods would just get completely bogged down by the sheer volume of this empty space between the data points. They'd struggle. SVMs, however, proved remarkably effective at navigating this high-dimensional space. It's partly down to their architecture, but especially their reliance on those support vectors and the maximum margin idea. They didn't need to model the entire vast empty space. They focused just on those critical points right near the boundary.
Ah, so they didn't get lost in the emptiness. They just focused on the important edges.
In a sense, yes. That made them highly suitable for complex data like text, with its huge vocabulary, or images with millions of pixels, or other signals where the feature count is massive. This inherent ability to conquer, or at least significantly mitigate, the curse of dimensionality was absolutely a key factor in their superstar status. It opened up possibilities for machine learning, especially with data types that were becoming more and more common, possibilities that were just out of reach for many other algorithms at the time.
Okay, so SVMs were great. Best linear separation, brilliant with high dimensions. But we started this by saying perceptrons failed because most real-world data isn't linearly separable. So even with maximizing margins and handling high dimensions brilliantly, how did SVMs actually break free from that fundamental constraint? Because, like we said, real data is messy, tangled. This is where you mentioned the mathematical booty of kernels comes in. Sounds like the secret sauce.
It really is the secret sauce. This is where the true ingenuity lies, and it's what really cemented SVMs as revolutionary. Kernel methods. They are a truly brilliant mathematical innovation. Fundamentally, what they do is allow SVMs to perform classification in a non-linear way. But, and this is the genius part, without explicitly transforming the data into what might be a much, much higher dimensional space. This clever concept is often called the kernel trick. Let's imagine for a second we could take our tangled, non-linearly separable data, remember the red dots inside the blue ring?
Yeah.
And imagine we could somehow lift it into a higher dimension. Maybe in 3D, if you imagine lifting those red dots up, creating a bump, suddenly a flat plane could slice neatly between the red and blue, right?
Okay, I can visualize that. Lifting it makes it separable.
Exactly. The kernel trick works on that principle, but with an absolutely astonishing computational shortcut. Instead of actually calculating and manipulating the coordinates of all the data points in this implied, possibly infinite dimensional feature space, which would just be computationally impossible, a kernel function computes something much, much simpler. It computes the dot product of the feature vectors as if they were already transformed.
Okay, dot product of the transformed feature vectors. That still sounds a bit dense. Can you give us a more intuitive picture? What does that trick actually do?
Absolutely. Let's try an analogy. Imagine a really complex handshake between two people. Instead of describing every single tiny movement of their fingers, palms, wrists in 3D or even more dimensions, the kernel trick simply tells you how strong that handshake feels. It measures the similarity or connection between two data points as if they were in that higher dimension, without ever needing to map out the whole intricate dance.
So it's like calculating the relationship in the complex space without actually going there.
Precisely. It's an elegant computational shortcut. It tells us if a simple separation could exist in some higher dimension, even if we can't see or explicitly calculate those higher dimensional coordinates directly. It's like, I don't know, sensing an object's shape in a dark room just by how echoes bounce off it without ever needing to turn the light on and see the object itself. And the power of this, you see it highlighted in foundational academic work, like the book Learning with Kernels by Sholkoff and Smola from 2002. It's a really key reference for SVM theory. This trick allowed SVMs to use different types of kernel functions. You have polynomial kernels for finding curved boundaries, or radial basis function kernels, RBF kernels, often called Gaussian kernels. They're good for more complex, sort of blob-like separations. Each kernel implicitly maps the data to a different, potentially incredibly high-dimensional space where suddenly a linear separation is possible. Yeah, so the kernel trick meant problems that looked impossibly tangled, interwoven, inseparable in our normal low dimensions. They could be elegantly separated in their implicit, higher dimensional representation, all just based on how the kernel function measured their similarity.
So if I'm getting this right, the kernel trick lets the SVM see complicated, tangled data in a new light, almost like looking at it from a higher dimension where a straight line could suddenly separate it.
Yeah.
But it does all this without actually doing the incredibly complex, messy, maybe even infinite work of transforming the data itself. That's quite a leap. Feels like machine learning magic, turning impossible problems into solvable ones.
You've got it exactly. The significance of this kernel trick, it really can't be overstated. It was the magic key. It unlocked SVM's true potential. It allowed them to effectively find sophisticated nonlinear decision boundaries. That made them incredibly versatile, capable of solving problems that were just utterly beyond reach for earlier algorithms. And this versatility, it also extended their use beyond simple binary two-class problems. There was research exploring multi-category support vector machines, like work by Lee et al. In 2001, to handle data with multiple classes. It just further solidified their position as a leading, really indispensable algorithm. It proved that sometimes the most elegant solutions aren't about brute force, but about finding these clever mathematical shortcuts that fundamentally change how you look at the data.
Okay, so with such powerful capabilities, maximum margin, handling high dimensions, this dazzling kernel trick, it's really no surprise. SVMs quickly found their way into a huge range of real-world applications. For a significant stretch of time, they weren't just promising. They were truly the gold standard of machine learning.
Yeah.
So where did they make the biggest impact? Which industries really got transformed by this?
Well, the sources give us some really crucial clues, especially when they contrast SVMs with what came later. There's that line, earlier methods might use handcrafted features like HOG or SIFT, and then feed them into, say, a support vector machine, SVM for classification. That single sentence actually tells us a lot about where they were used.
HOG and SIFT, what are those?
Right, so HOG stands for histograms of oriented gradients, and SIFT is the scale invariant feature transform. These are classic examples of what we call handcrafted features. Basically, these were clever ways humans designed to give computers a head start in seeing things in images. HOG, for instance, would look for patterns of light and shadow, like edges, helping a machine detect object outlines. SIFT identified distinctive landmarks in an image that stayed recognizable even if the image was scaled or rotated. Researchers would painstakingly design these feature extractors, run them on images.
And then feed that extracted information into the SVM.
Exactly. The SVM did the final classification based on those human-engineered features. So this whole approach tells us SVMs were heavily adopted in fields needing sophisticated image classification, object recognition, pattern recognition. Think about applications like medical imaging, identifying anomalies in X-rays, MRIs for early disease detection. Hugely important.
Right, critical stuff.
Absolutely. Then there was facial recognition. Those systems were gaining traction back then, identifying people, verifying identities. SVMs were often behind the scenes. Document analysis was another big one, recognizing handwritten characters on bank checks, sorting postal codes. You know, early CNNs like Lynette showed promise there too, but for many years, SVMs often provided a really robust, sometimes better solution. But it went way beyond just computer vision. SVMs found homes in areas like bioinformatics, classifying genes, proteins, helping researchers understand diseases, predict protein functions.
Wow, okay. Biology, too.
Yeah, and medical diagnostics more broadly. Identifying complex disease patterns from patient data. They were also crucial in early natural language processing, text categorization, sentiment analysis, and notably, really effective spam detection.
Well,
We can thank SVMs partly for cleaner inboxes.
okay, appreciate that.
And in financial modeling, things like fraud detection, credit scoring, predicting market trends, areas where robustness and accuracy are absolutely paramount, SVMs were deployed there. Even manufacturing for quality control, classifying defects in products on an assembly line. Their ability to deliver high accuracy, often with relatively smaller data sets compared to what deep learning models need today, made them invaluable across this incredibly broad spectrum. It really cemented that gold standard status. They were a cornerstone of practical, deployable AI for well over a decade.
That was clearly an era before the widespread adoption of what we now call deep learning. And in that landscape, where computing power wasn't infinite, where you needed theoretical guarantees, robust performance on complex, feature-rich data, SVMs really did offer this almost unbeatable package, didn't they? It's hard to imagine how much progress might have stalled without them.
Absolutely. If we connect this back to the bigger picture, SVMs provided these robust, theoretically well-grounded solutions for so many problems that were just intractable or handled poorly before. They really showcased the power, the practical applicability of statistical learning theory for real-world scenarios. That ability to generalize well, even with complex, high-dimensional data, made them indispensable across so many industries and research areas for, easily over a decade. They bridged that gap between mathematical elegance and practical utility in a way few algorithms had before. Firmly established their gold standard status, enabled real-world AI applications to really flourish.
But as with all superstars, right? In tech, in science, the spotlight eventually moves. The sources talk about a departure from earlier methods, like SVMs. This led to the rise of entirely new paradigms and ultimately the dominance of neural networks. So what were these limitations? What finally nudged SVMs aside? Was it that they just weren't good enough anymore, or was something bigger going on?
That's a really good point, and it's important to frame it correctly. The limitations that eventually gave way to neural networks weren't necessarily like fatal flaws in SVMs themselves. SVMs are still powerful, still effective for many, many tasks today. It was more a story of the landscape changing around them. Rapid evolution of technology, emergence of algorithms capable of even greater feats, especially, and this is key, when you feed them exponentially more data and throw massive amounts of compute power at them. The ground shifted dramatically. It created this kind of perfect storm for a new breed of algorithms to take center stage.
Okay, a perfect storm. What sparked that? What are the key ingredients that ended the SVM reign?
Well, we entered this new era, really starting around 2012. That's when deep learning approaches started to dominate. It marked a truly significant shift, especially in areas like image recognition, where SVMs, using those handcrafted features, had been king. The key catalyst, the big watershed moment, was a specific type of neural network, a convolutional neural network, or CNN, developed by Krzyzewski and his colleagues. It's commonly known as AlexNet. AlexNet achieved this unprecedented victory in the big ImageNet Image Classification Challenge in 2012. It won by a large margin.
I remember hearing about that. It made huge waves.
It really did. This model, it just demonstrated the immense power of deep learning. It had, I think, 8 learned layers, trained on millions of images, and it achieved unprecedented accuracy. It frankly shocked the AI community, opened everyone's eyes to what was suddenly possible. And a critical difference, a fundamental shift, was that these deep neural networks could learn increasingly abstract features from the raw data
Automatically, unlike the handcrafted HOG and SIFT.
Exactly. That was a profound departure from earlier methods. Instead of human engineers painstakingly designing feature extractors, essentially telling the computer what patterns to look for, deep networks could discover the most relevant features directly from the data itself, through multiple layers of processing.
So it learns how to see, rather than being told what to look for.
That's a great way to put it. It's like the difference between giving an artist incredibly detailed instructions on every brushstroke versus an artist who learns to see and intuit the most important forms and textures on their own. This end-to-end learning, from raw pixels to final classification, that was the game changer. Now, it's worth remembering, as you mentioned earlier, early CNNs like Linnet were used for things like recognizing handwritten digits on checks way back in the 1990s, so the potential was there.
Right, the seeds were sown earlier.
They were. But the true deep learning explosion around 2012 was enabled by a confluence of factors. We finally had truly large data sets, millions, even billions of examples. We had powerful GPUs, graphics processing units, initially for gaming, but perfectly suited for the parallel computations needed to train deep nets. And there were significant algorithmic innovations, too, things like the RealU activation function, techniques like dropout to prevent overfitting. So modern CNNs became much deeper, often having dozens of layers. They could leverage these massive data sets and powerful GPUs to tackle very complex tasks. The whole movement was towards systems deliberately designed not to start with a representational system. Let the raw data flow in, let the network figure out the representations. Allow the data to be filtered by neural network systems to produce these incredibly powerful outputs. That fundamentally changed how features were learned and used. And ultimately, it led to that departure from earlier methods that had defined the SVM era. The sheer power of automatic feature learning on massive data combined with computation. It just unlocked a new level of performance that SVMs, for all their mathematical elegance, couldn't quite match in many, especially perceptual domains.
So wrapping this up, what does this all mean for us today? SVMs, okay, maybe not the reigning superstars anymore, but they represent this absolutely critical phase, right? In the whole evolution of machine learning. They took us way beyond the limitations of those early perceptrons. They provided powerful, mathematically beautiful solutions at a really crucial time, a time when maybe the compute power and the sheer data volume needed for today's deep learning just weren't there yet. They were the essential bridge.
Absolutely. Their legacy is undeniable. They cemented the importance of core concepts like margin maximization, that idea of building robust classifiers. They introduced the transformative power of kernel methods, showing how you could tackle nonlinear problems cleverly without explicit, costly transformations. And SVMs proved especially effective for that tricky, high-dimensional data, making them invaluable for years in fields from computer vision to text analysis. Their principles, they still inform and inspire research today. And they remain just a foundational piece for anyone wanting to understand the progression of machine learning, a real testament to how elegant mathematical ideas can solve really pressing real-world problems.
This whole journey from perceptrons to SVMs and now to the dominance of deep neural networks, it just perfectly illustrates how dynamic AI is, constantly evolving. It really makes you wonder, doesn't it? Given this constant cycle of superstar algorithms, shifting gold standards, what are the current AI darlings? Maybe things like today's large language models, the ones that caused such huge excitement in the AI community back in 2019 with models like T5 and GPT-2, and now they're everywhere. Will they eventually be seen as foundational? Yes, but maybe limited in ways we can't yet see by the next generation of breakthroughs.
That is the important question, isn't it? In a world moving at this rapid pace of development, where technology can literally transform the world beyond recognition within a human lifetime, what are the lasting lessons we'll draw from today's cutting edge? The history of SVMs is such a great reminder that even today's gold standards are often just sophisticated stepping stones. Each brilliant in its own time, absolutely crucial, but ultimately paving the way for further, sometimes completely unprecedented change. It makes you think, what current limitations are we perhaps blind to? What unseen linear separability problem are today's models hitting that some future Minsky and Papert, or maybe a future Vapnik and Cortez, will illuminate, sparking the next huge leap? It's a humbling thought, but also incredibly exciting, looking down that unpredictable path of AI discovery.